Okay, as stated in the last video, we talked about what a null and alternative hypothesis are. Now we're going to go ahead and look at some intuitive examples involving these ideas, and eventually we'll take that idea, come up with a more formulaic process, and then look at what we call significance tests. Okay, so first we're just going to think about all these ideas intuitively, and remember in the last video we ended with the example where we had a null hypothesis that the mean was equal to 2.983, an alternative that the population mean was less than 2.983, and then we had a standard deviation of 2.5. Okay, so what we're going to do is we have a few statements, and we'll determine which of the following statements provide evidence that BC students really have a lower average than the nation. We will also want to figure out if we have, this should say strong evidence. So if we have strong evidence for that, or if it's maybe weak. So we're kind of going to look at many different scenarios with this. Okay, so for the first part, part A, says in this study we take a simple random sample of 100 BC students. So this means that we have n equaling to 100. Okay, it also says the average amount of TV watching, so from those students, is at 0.95. So we know x bar is equal to 0.95. Okay, we were given before that mu was equal to, our null hypothesis is that it's equal to 2.983, and that our standard deviation was 2.5, so if we adjust our standard deviation, we're going to have 2.5 over the square root of 100, which is really just 0.25. Okay, so basically what we're thinking about here is our population mean equaling to 2.983 really going to be accurate? And what I'm thinking right now is, you know what, if I am hypothesizing that's my population mean, but then I test some sample to figure out if that's true, I see from this sample that the mean of the sample was 0.95, which seems like it's quite a bit different from 2.983. So I don't think that this is really going to be an accurate measure, but what we can do is look at this mathematically and intuitively think about if it will be accurate or not. So to do that, what I'm going to do is just draw a bell curve. Okay, I know that my mean on this bell curve is 2.983. Okay, and then I know that I have some x bar value over here, which is 0.95. What I'm going to look for is this little p-value. So the reason I'm looking for this p-value is because I know if this p-value is really small, it means that 0.95 is way over here. So it means it's way different than our population mean, which means that my null hypothesis that the population mean is equal to 2.983 is probably not that accurate. So that's kind of what we're thinking about with this. So now I'm just going to calculate this little probability. If I do so, I need to find the z-score. I have z equals 0.95 minus 2.983 over my adjusted standard deviation, which is 0.25. Okay, and if I do the calculator work there, that's negative 8.132. Okay, so now I know if I went to look this up, I would just assume that this part's 5, so we'd look up, but we'd really just kind of round to 0.5. Okay, so not 5 but 0.5. Okay, so I'd look up, I'd round that to 0.5, okay, on this piece, and that's because, remember, if you have something above 3.4 to 3.5 standard deviations, we can just round up for that. So what this would mean is the probability that x bar is less than 0.95 is equal to 0.5, so this whole piece, minus 0.5, which is 0. So what this tells me is, yeah, actually 0.95 is really far away from 2.983. I can see that with how big the standard deviations away from 2.983 are, but I also see that with my little p-value. So this teeny little p-value tells me this value is slid all the way over here. It's really far from 2.993. So now if I thought, oh, my population average is this, but then the sample I pulled is way different than that, then I would reject that my null hypothesis was really equal to this, and I would accept the alternative. So I would think, you know what, it probably is going to be less than that, or it should be, because this is just too far away from 2.983. Okay, so to explain that a little bit more, okay, we would say we have strong evidence that the population mean is probably not equal to 2.983. Okay, so we would say our result is statistically significant. Okay, and this is because 0.95 is really far away from 2.983. Okay, so this means that it would be very unlikely that 2.983 is truly the population mean. It's truly the population mean. Okay, so based on that sample I pulled is really far away from 2.983, so I don't think that that's actually going to be the average. So I would guess that the average would be lower than that based on that sample. Okay, so now let's go ahead and look at another example. Almost everything's going to be the same, but we're going to see how this kind of unwraps into maybe not having something that's significant. So we're going to look at a couple more of these with the same intuitive idea. Okay. So next part says we take a sample of 100 BC students. The average TV watching for that sample is 2.45 hours. So from this, we can gather that n is still 100. This time our x bar is 2.45. Our mean is still 2.983. And our adjusted standard deviation is still going to be 0.25. Okay, so that just follows from part A. All right, so I'm going to use the same idea. Here I'm thinking 2.5 is kind of far away from 2.983, but maybe not that much. So I'm just going to have to look at this numerically to really take a guess as to what's going on with this one. Okay, so let's draw a curve out. I see that my mean is centered and it's 2.983. And then that's my population mean. My little sample mean over here is 2.45. Okay, I'm going to focus on this p-value. If this is really tiny, I know this line must be far over here. If it's pretty big, then I know I'm moving closer to the mean. So here, let's find our p-value. So I'm going to have z equals 2.45 minus 2.983 divided by adjusted standard deviation, which is 0.25. If I do the calculator work there, I would get about negative 2.13. Okay, so if I look that up, I would get 0.4834, and that's just looking that up on the table that I've been using for the notes. Okay, so that tells me that this little piece right here is 0.4834. So I know the probability that x bar is less than 2.45 is equivalent to this 0.5 right here minus this chunk right here, so 0.5 minus 0.4834, which gives us 0.0166. Okay, so what I'm thinking intuitively for this is the 2.45 isn't super far away from 2.983, but it's pretty far, a little bit more than 2 standard deviations. It's fairly far away, and I can see that's reflected in this p-value. So this p-value says, you know what, this little guy, this area right here is going to be small, so I know this line has to be pretty far over. So what this tells me is that it's likely that my sample mean is pretty different from my population mean, so maybe the population mean isn't as accurate. So I would probably still reject the population mean being equal to 2.983 on this, but I don't have as strong as a result as I did in part A. So I'm going to write that out. Okay, so what this means is we might be able to reject the null. So we might be able to reject the null hypothesis since 2.45 is a fair distance from the mean, so from the population mean of 2.983. Okay, however, this wouldn't be as statistically strong as part A. So however, not as strong as part A. Okay, so if we look in part A, what we just computed, we're like, whoa, those are way different. I don't think this is going to be accurate as equal to that if it's that much different. Okay, here I'm saying, there's some difference that's kind of far away, but maybe not as far away. So here we might be able to reject the null hypothesis, but it's not going to be as certain as it would have been in part A. Right, so now let's go ahead and look at one more. Oh, hang on one second here.